All right, guys, in this video, we're going to cover buffer reactions and titration curves and more of conceptual questions having to do with titrating a weak acid with a strong base. Now, it's important to understand the buffer curve. So in the beginning, you have the initial pH of that weak acid. That can be determined by just doing the ice chart with that weak acid. The buffer region, after you increase the volume of strong base that's added, can be figured out by determining the moles of NaOH that are added using the molarity and the volume, and subtracting that from the initial moles of the weak acid. Doing this and modifying the ice charts and modifying the volumes can determine your new concentrations, in which then an ice chart or the Henderson-Hasselbalch equation can be used to figure out the pH. Then the equivalence point, which means the volume of NaOH and really the moles of NaOH or the strong base, whichever one it could be, but mostly NaOH, is equal to the moles of the weak acid. This means you have a complete neutralization of the weak acid, and the pH of this solution is determined by the conjugate base. You have to use the Kb and do an ice chart with the Kb. Anything beyond that point, so any amount of NaOH or strong base beyond that point, the pH can be determined by the excess of that base after you subtract the moles of that base from the initial moles of the weak acid. So let's say there's 1 mole of weak acid, and after at 12 milliliters of NaOH, there is 1.5 moles of NaOH. The way to determine the pH would be take the 1.5 moles of NaOH, subtract the 1 moles that it would neutralize of the weak acid, which means that our 0.5 moles of NaOH will be remaining. This means that our pH can be determined by just taking the negative log of 0.5. That would give us the pOH. 14 minus that pOH value will give us the pH. So now going on to specific questions. And if we have question number 10 here, where it says 100 milliliters of 0.1 molar acetic acid, this is a weak acid, are mixed with 80 milliliters of 0.1 molar barium hydroxide. So the question is, what determines the pH after the reaction? First, we need to fill out or figure out the moles of each of the weak acid and the strong base. Now, the moles of the weak acid you can figure out by doing 0.1 times the volume of 0.1 liters or 100 milliliters. And that gives us a value, which I will write on the PowerPoint slide just so we have it, 0.1 moles. Now, for the barium hydroxide, we have 0.08 liters times 0.1 molar. Now, that needs to be multiplied by 2 because we have 2 hydroxides for every barium hydroxide. So that would be 0.008 times 2, which is 0.016 moles. So that would give us the moles of OH, which is important for determining the pH. Now, comparing these mole values, we have more of the strong base. We have more of the hydroxide, which means that the acid will be completely neutralized, and the excess will be 0.008 moles of OH in excess. This means that the pH is determined just by the presence of the strong base. So that would be the answer there. Going forward, question 11. We have double the concentration of acetic acid, which means our new moles is 0.02. And we're being mixed with 50 milliliters of 0.2 molar HI. Now, HI, unlike the previous question with barium hydroxide, HI is a strong acid. So you're mixing a weak acid and a strong acid. We don't even have to do math for this because we know that a weak acid is going to contribute not much at all to the pH, or specifically to the dissociation of hydrogens in comparison to a strong acid, which contributes 100% of its molecules with dissociation of hydrogen. This means the pH will be determined by just the presence of strong acid. Next, number 12, we have a acetic acid again mixed with NaOH. So we have the weak acid mixed with the strong base. So the amount of moles are going to be 0.1 times 0.02, or sorry, 0.1 times 0.2, which is 0.02, so the same number of moles that we had in the previous question. The moles of NaOH, on the other hand, will be 0.05 milliliters, or liters, times 0.1. That would be 0.005. So let's write that down, just so we know. We have 0.005 moles of the base. This means that we have less base than the weak acid, which means, according to our graph, we're going to be in the buffer region, because the equivalence point is where the moles of NaOH equal the moles of the weak acid. In this case, we're not equal yet, we're still less. So we're in the buffer region. The buffer region can be determined, or the pH in the buffer region can be determined by the Henderson-Hasselbalch equation after you do the subtraction. So what we have in terms of what determines the pH would be the buffer of the weak acid and its conjugate base, because we have the weak acid still present, which is the acetic acid, and the conjugate base is going to be the amount of weak acid that is converted to conjugate base by the neutralization by NaOH. Number 13, very similar amount. We have the same amount of acetic acid, 0.02, are mixed with now more NaOH. And this is going to be the same amount of NaOH, so 0.02 moles of NaOH. If you do 0.05 times 0.4, that's 0.02. So now, since the moles of NaOH are now equal to the moles of weak acid, we are now at the equivalence point, which means to determine the pH, it is just the conjugate base. So we would find the Kb for acetic acid, and we would do an ice chart with the weak acid, or with the conjugate acid for the weak base. Or sorry, the conjugate base for the weak acid. So the answer would be conjugate base. Number 14, we have acetic acid, but in this case we have 0.01, so we have less moles. So I'm going to write that number down, 0.01, and we're mixing it with, looks like 0.01, hold on, 0.01 liters times 0.1 is 0.001. 0.001 moles of strong base. So in this case, we have less base than we do weak acid, which means we're still in the buffer region, and the pH can be determined with the Henderson-Hasselbalch equation. So the pH can be determined since it is a mostly weak acid, and then a little bit of the conjugate base that is neutralized by the added NaOH. Number 15, we have 100 milliliters of 0.2, so that means our moles are going to be 0.02. And we're mixing it with 0.024 moles of the NaOH. And sorry, my numbers are getting a little bit sloppy here, but we just want to write those down to compare them. So since our NaOH is larger than the amount of weak acid, it would be the weak acid will be completely neutralized, and we'll end up with an excess of 0.004 moles of excess, and that excess is of the strong base, meaning the pH can be determined by the strong base alone. Number 16, we have a different acid, but it's still a weak acid, so it doesn't really matter. This is formic acid. We have 0.02 liters times 0.25 molar. That gives us a mole value of 0.005. Comparing that to the amount of strong base, which is KOH, and it's 0.01 liters times 0.5 molar, gives us the exact same amount. So these numbers are equal, meaning there is a complete neutralization of the weak acid, meaning the equivalence point has been reached, and the pH of the solution can be determined by using the Kb of the conjugate base of the weak acid and doing an ice chart with that value. Number 17, we don't need to write numbers for this one, and we'll see why. We have a certain amount of NaOH mixed with a certain amount of HCl. So what determines the pH after the reaction? Now, actually, we do need numbers. We need to compare them. we can figure out the moles of NaOH, and these are strong acid, strong base now. So we're not even going to be looking at this pH titration chart. So our moles of NaOH are going to be 0.0125. Our moles of HCl are going to be 0.012 times 1 molar, so 0.012. So our base is in excess by a little bit of the acid, by 0.0005 moles. So since our NaOH is in excess, it will completely cancel out the strong acid, and the remaining will be the NaOH, which can be used for the pH. So now let's just go through and we'll submit our answers and make sure they are right. We did number 10. You see that's right. Number 11, number 12, number 13, 14, 15, 16, 17. Okay. If you have any other questions about titrations and buffers, please comment below. There are other videos that I have on ice charts and dealing with a weak acid, strong base titrations. So please take a look at those, and I will put a link to one in the description below. So thank you, and happy studying.